assistant professor at the University of Texas at Austin. Today I'm going to present a paper from our research group titled The Impact of Climate Change and Envelope Retrofit on Urban Energy Consumption, Comfort, and Overheating in Austin, Texas. Austin is now one of the fastest growing cities in the US. This increase in population, coupled with climate change projections, will likely increase energy demand, especially for cooling, dramatically in years to come. As over 30 to 40% of greenhouse gases come from the built environment, many local governments are setting ambitious targets to reduce this impact, including Austin. Our strategy in this project is to retrofit existing buildings for greater energy efficiency while also examining the conditions that would occur during a blackout situation. Recent findings have made it clear that common energy use mitigation strategies may not have lasting efficacy in the impending climate conditions. Therefore, it's pertinent to measure not only the energy performance of the building stock, but also the livability of the indoor environment in the case of a natural disaster, for example, that could cause a blackout. To accomplish this, we superimpose a climate scenario for the 21st century as projected by the Intergovernmental Panel on Climate Change with building refurbishment and evaluate both urban energy demand and building overheating in the West Campus neighborhood of Austin, Texas. We combine a GIS database of Austin buildings with CitySim, a large-scale urban energy simulation tool that takes into account the urban area and surrounding buildings using Rhino and Grasshopper. The database contains footprints, heights, year built, as well as building use type. The final West Campus neighborhood consists of 651 buildings that we simulate. We used a year-built approximation to generate construction material properties. Each material group contains a different set of wall, window, and roof assemblies. For the refurbished case, we use wall, roof, and window materials reflecting LEED Gold material standards. In short, the process consists of collecting all the building information in Grasshopper, such as geometry, material information, occupancy information, and shading and ground surfaces, so that Grasshopper CitySim can write a CitySim markup file to be used for the simulation. This figure shows the average daily temperatures, including highs, means, and lows across the entire year in Austin for 3 different climate scenarios developed by the IPCC. We use the B1 scenario and assume for refurbishment cases that the entire building stock would be retrofitted by 2040. Here we consider first the no refurbishment case. As you can see, energy use increases dramatically after 2040. You see an energy consumption increase of 48% by 2040, and by 2100, an overall energy increase of over 67%. Here you can see that improving the wall material has a modest impact. And finally, improving the glazing has a greater impact than just improving the walls. But the only case where you could see an overall energy consumption decrease is in the case of a full refurbishment, where you refurbish both the glazing and the walls. So in summary, in the no refurbishment case, buildings consume 67% more energy for cooling by 2100, and the full refurbishment decreases energy use by as much as 13% by 2040. For indoor temperatures, we simulate the case of an ongoing electrical blackout, an occurrence that we expect to increase in frequency and severity due to climate change and natural disasters. So the resulting potential for overheating in buildings can, as we know, create life-threatening conditions, especially in vulnerable populations. Therefore, we consider this very important to consider. The full refurbishment case, we can see increases overheating most dramatically. In this case, it's very exaggerated. And we think this is due to retention of heat from the higher insulation. In 2100, indoor high temperatures averaged 41.7 degrees Celsius across all buildings, a 4.6-degree increase over 80 years. This represents an increase of more than 50% over those without refurbishment. With refurbishment, the upper quartile of buildings averages 42.7 degrees Celsius during the hottest 90 days. Extreme indoor temperatures in the upper quartile rise over 68% more rapidly than in the non-refurbishment case. We identify a correlation between building type and propensity for overheating. The division is clear in all three cases, but is especially pronounced in the 2100 refurbishment case, which, unlike other cases, contains no variation in material throughout the building stock. Multi-family housing buildings, which comprise most of the massive buildings in the neighborhood with the lowest surface to volume ratio, perform most favorably in this case. Both types of building qualities discussed in this paper, envelope material and building typology, have an impact on building performance and disaster risk mitigation in Austin. Our results suggest that retrofit of material alone is not a sufficient response to meet future performance goals. On the other hand, the relative high performance of the multifamily residential buildings show that those buildings yield a general improvement over most others. They are not only more energy efficient, but also less prone to the extremes of overheating in an ongoing blackout situation. Thank you very much.